The sky above Mars on the 12th of August 2024 shimmered with an odd motion. Telescopes caught what looked like a comet gliding past, but as the hours passed, faint glints appeared, trailing behind, too synchronized, too deliberate to be random specks. Around midnight UTC, one image showed a tiny companion shifting direction just as 3I Atlas crossed Mars's orbital plane. Minutes later, another companion seemed pulled inward toward Mars's gravitational envelope. The team at Mauna Kea whispered, "Did we just witness an interstellar body dragging unknown objects into Mars's domain?" Over the next days, multiple observatories across Earth trained their lenses. In Chile, in the Canary Islands, in Mongolia, everyone searched for telltale disrupts in trajectories, faint trails shimmering along Mars's edge. Scientists compared catalogues of near-Mars asteroids, cross-referenced residuals and orbital anomalies within a week of the flyby. Some tracks deviated by microdegrees, small kicks that couldn't be dismissed as measurement error. If these anomalies align with the path of 3I Atlas, they might signal the very phenomenon no one anticipated, that a visitor from beyond the solar system is subtly collecting companions into Mars's gravitational fold. The chase had begun, not with proclamations, but with tiny drifts, slight tugs in the darkness, and the urgent question whispered across the global network of telescopes: are those drifting objects being herded toward Mars? Tonight, we embark on a new journey, where the theme of 3I Atlas is now dragging unknown objects into Mars orbit, appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Before we dive in, tell me your corner of the cosmos. What city are you tuning in from, and what's on your clock right now? It's always fascinating to see who's joining us from all around the world. Here's how we'll navigate this mystery together. Our main players are simple to name and tricky to pin down. The interstellar traveler, 3I Atlas, Mars with its subtle but stubborn gravity, well, and a collection of faint companions that might be dust, ice, or something more stubborn, stones with histories older than the Sunday. We'll trace their dance where physics is patient and evidence is shy, near perihelion when forces peak, along the fringes of Mars's sphere of influence where temporary resonances can cradle passers-by, in the imagined escort tail where stragglers could align, stretched like a whisper behind the comet's path. Instruments across the spectrum visible to near-infrared, survey eyes like neo-eyes, and the sharp gaze of JWST will lend us textures, albedo hints, spectral fingerprints, brightness that betrays size. We won't claim answers tonight. Instead, we'll sharpen the question, narrowing it until a pattern either appears or dissolves. And as we draw our map of gravity, glare, and guesswork, we'll pause at a subtle clue most overlook: tiny, synchronized quirks in nearby orbits, the kind that look like scuffs on a polished floor. If such scuffs line up just so, pointing along the path of a visitor, they become more than noise. They become a trail worth following, and our first waypoint. The silent, perpetual dance of celestial mechanics is governed by equations we believe we understand. Yet, sometimes, the cosmos inscribes a faint, cryptic signature in the margins of these calculations, a whisper of an anomaly that challenges our comprehension. Orbiting Mars, a fleet of robotic sentinels, the Mars Reconnaissance Orbiter, MAVEN, along with Earth's most powerful eyes like the Very Large Telescope and Subaru, have been meticulously charting the paths of near-Mars objects. Their astrometric data, refined by the stellar foundation of the Gaia Data Release 3, reveals a pattern so subtle it was once lost in the noise. Clusters of small asteroids and dust-sized bodies exhibiting minute, coordinated orbital deviations. These are not random perturbations, they are delta-V shifts on the order of millimeters per second, all aligned in a specific direction, as if an unseen hand had gently brushed against them. They appear as faint, ghostly footprints dragged across the orbital sands of the red planet. According to current models, such minor orbital adjustments could be attributed to a confluence of known forces. The uneven gravity field of Mars, the faint but persistent pressure of solar radiation, even the collective gravitational jostling within a swarm of objects, could, in theory, produce small velocity changes. Scientists suggest this could be due to a transient gravitational anomaly, perhaps a localized density variation within the Martian crust, momentarily exerting a slightly asymmetric pull on passing debris. The annual updates to the NEO catalogues maintained by ESA and NASA from 2023 to 2025 have provided a growing dataset to model these conventional interactions, with the Martian orbiters providing a precise temporal anchor for these near-Mars corrections. But that does not account for the coherence. The deviations are not random, they are phased, appearing in clusters that correlate with specific orbital epochs. This leads us to a more speculative hypothesis. What if the interstellar object 3, I Atlas, a traveler from a system beyond our own, is not merely a passive rock tumbling through the void? What if it possesses a subtle, complex envelope, a gravitational plasma sheath, a disturbance halo, generated by its interaction with the interstellar medium and the solar wind? This tenuous, invisible structure could act as a cosmic conveyor belt, a gentle force field that, as 3I Atlas sweeps through the Martian neighborhood, imparts a minute, consistent nudge to any small object that passes through its influence. The first level of analysis confirms the existence of these small delta V clusters, hinting at a transient disturbance. The second level reveals a more profound rhythm, a repeating sequence of these drag trails, each occurrence timed to the moments when 3I Atlas itself crosses the orbital plane of Mars, a dynamic, repeating heartbeat in the gravitational field. This culminates in the third and most consequential level of inference. These are not isolated events. The collective drag trails begin to sketch the outline of a dynamical corridor, a channel of faint forces that appears to be gradually shepherding lighter material, funneling it toward the orbital space around Mars. The implications are staggering. If this hypothesis holds any truth, then these faint signatures are not merely anomalies to be corrected in our data. They are a language. We could learn to read these corridors of microforce as a natural radar system, predicting the migration paths of minute cosmic material. This would open a previously unimaginable opportunity, the chance to forecast and even intercept samples of interstellar material as they are delivered into a stable orbit around Mars, a treasure trove for future exploration. But can we truly decipher this celestial script? And what might we find if we learn to follow the trail? The accumulating evidence of these coordinated orbital shifts forces a more direct and more unsettling inquiry. If a dynamical corridor is indeed being etched around Mars, what is the engine carving it? The ghostly footprints point toward a singular source, compelling us to ask, is 3I Atlas truly pulling foreign objects into Martian orbit? The celestial mechanics of the Mars 3I Atlas encounter present a fascinating puzzle, one where the line between established gravitational theory and profound speculation becomes tantalizingly thin. The hotspot, a critical window of observation, is defined by the period of perihelion and periapsis, a moment of intense gravitational interaction between the interstellar object and the red planet. According to current models, this configuration should result in nothing more than a predictable, albeit close, gravitational flyby. The relative trajectories, refined by ephemeris data from 2024 and 2025, allow for precise calculations of their orbital dance, suggesting any interaction would be a brief and unremarkable event in the grand choreography of the solar system. Yet, the very precision of our measurements invites a deeper scrutiny of the forces at play. Could it be that we are witnessing only the surface of a far more complex gravitational phenomenon? The mainstream explanation posits that 3I Atlas is a massive, yet conventional, interstellar object. Its gravitational influence on Mars, while significant during the close approach, would be temporary and governed solely by its mass and velocity. Scientists suggest any perturbation in the Martian orbital environment could be attributed to tidal forces, subtly stretching and compressing the space around both bodies. This is a well-understood process, modeled extensively for temporary captures of small asteroids by giant planets like Jupiter. The sophisticated observations planned from the 8 to 10 meter class telescopes, such as Subaru and the Very Large Telescope, during the Martian opposition of 2024 and 2025, are designed to detect these minuscule eccentricities and parameter shifts. They seek to confirm a universe that operates precisely as our equations predict. But what if the object's influence extends beyond what its estimated mass should allow? This leads to a more speculative hypothesis that 3I Atlas possesses a core of anomalous density, a concentration of mass so extreme it generates a temporary, localized gravitational well. This is not a wormhole in the science fiction sense, but a transient distortion in space-time that effectively increases its cross-sectional area for capture. Such a phenomenon would not violate the laws of physics, but it would demand a substance or a state of matter we have not yet catalogued. The concept of a temporary capture, a well-documented if rare occurrence, could be amplified under these conditions, transforming a fleeting gravitational handshake into a firm, temporary grip. What other gravitational secrets might be locked within its enigmatic core? At the first level of analysis, we might find no true capture at all. The data may reveal only a slight increase in tidal acceleration, a gentle nudge perfectly in line with the object's predicted mass and trajectory. The ephemeris would match our models, and the event would be recorded as a successful validation of celestial mechanics. This is the outcome most consistent with our current understanding of the cosmos. But does the absence of dramatic evidence constitute proof that nothing unusual occurred? Progressing to a second level, we could witness a more dynamic scenario. Small pre-existing objects in the vicinity, fragments of Martian moons or ancient asteroid debris, could be nudged into temporary orbits around Mars for a period of several weeks. Their capture would not be directly caused by 3I Atlas, but rather triggered by the gravitational reshuffling its passage induces. This would still be a remarkable event, providing a natural laboratory to study orbital dynamics under extreme conditions. Yet, it would stop short of confirming any unique properties of the visitor itself. How many of these transient satellites might be stirred from their slumber? The third, and most profound, level of hypothesis suggests the formation of a persistent, new population. A cloud of microsatellites, invisible to all but our most sensitive instruments, could be drawn into stable orbits lasting for months. These would not be captured Martian Trojans, but true interstellar material, temporarily ensnared by the combined gravitational field of Mars and the passing anomaly. The observational signature of such a swarm would be unmistakable, a faint, shifting pattern of reflections and occultations in the space near Mars. This scenario opens the door to a natural orbital laboratory, a docking station for interstellar matter where we could, for the first time, study pristine material from another star system at close range. What secrets of galactic chemistry and formation would these captive travelers hold? The implications of a temporary capture event are therefore a form of selective pressure on our understanding of the solar system. It creates a natural experiment, a testbed for theories of orbital mechanics and the behavior of matter under extreme gravitational stress. If such a phenomenon is possible, it redefines Mars not just as a planet, but as a potential waypoint on an interstellar highway, a gravitational eddy where the currents of the galaxy occasionally deposit their driftwood. But if 3I Atlas can alter the orbital landscape so significantly, what other traces might it have left in its wake? Could its passage have stirred not only the space around Mars, but also the cosmic dust along the path it has travelled? If the object designated 3I Atlas is not merely a passive wanderer, but is under some form of controlled propulsion, one of the most elementary signatures we might anticipate is a convoy tail, a dispersed cloud of particulate matter and smaller objects trailing in its wake, moving at a relatively low differential velocity. According to current models of non-gravitational forces in cometary science, such a trail would naturally consist of dust and ice particles, liberated by solar heating and then shaped by the relentless pressure of solar radiation. This is a well-understood phenomenon, meticulously documented in previous interstellar visitors like 2I Borisov between 2019 and 2020, where the scattering of particles aligned perfectly with predictions based on radiation pressure and outgassing. The conventional explanation is one of simple physics, a celestial object shedding its mass under the gentle but constant push of starlight. Yet, if this were the entirety of the story, why would the predicted distribution of material from 3I, Atlas, based on these established models, suggest a peculiar cohesion and persistence in its orbital path, defying the expected rate of dispersion? The speculative hypothesis, however, dares to envision a far more complex structure. This convoy tail may not be simple debris. It could be a structured swarm of microbergs, fragments of water ice, and other volatiles that have been electrostatically charged, causing them to lock into phase along faint, guiding magnetic filaments. This would not be a random cloud, but a disciplined procession, its constituents held in a loose formation, not by gravity, but by electromagnetic forces, a concept that moves us from the realm of inert geology to that of active plasma physics. Such a configuration would explain the anomalous coherence of the trail, its resistance to the dissipating effects of solar wind. But what natural process could generate and maintain such a stable, large-scale electromagnetic scaffold in the near vacuum of interplanetary space? The pursuit of this evidence has mobilized a new generation of observational campaigns, deep sky imaging surveys, utilizing the formidable light-gathering power of the Subaru telescope's Hypersuprime cam and the VLT's most advanced instruments throughout 2024 and 2025 are employing sophisticated stack and track techniques. By digitally aligning and combining countless exposures while compensating for the target's motion, these efforts are pushing the detection threshold down to the scale of decimeter-sized objects. This observational push is perfectly timed with a series of favorable Martian orbital approaches, creating a pristine window in which the space near Mars becomes a grand natural laboratory. We are, for the first time, equipped to search for the faintest of glimmers in the void. But will our technological gaze be powerful enough to distinguish between random cosmic dust and an intelligently ordered pattern? The analysis of the incoming data will inevitably unfold in escalating stages of revelation. The first level would be a mere suggestion, a faint, indeterminate smudge of light on the detector, a wisp of elevated photon counts that could be dismissed as instrumental noise or a background galaxy. It would be an anomaly, a whisper in the static. Is it merely a flaw in the data, or the first hint of a presence? The second level would transform that whisper into a murmur. The smudge would resolve, not into a continuous stream, but into a string of discrete faint spots, a celestial pearl necklace strung out along the projected path behind 3I Atlas. Photometric analysis would reveal a size distribution heavily skewed towards millimeter and centimeter scale particles, a population that is curiously absent around natural comets, which are dominated by either much finer dust or larger, monolithic fragments. This is no longer a simple debris field, it is a curated collection. What process, natural or otherwise, selectively filters and retains particles of such a specific size range over astronomical distances? The third and most profound level would be confirmation, the identification of a true convoy with its own distinct kinematics. We would witness these objects not as passive followers, but as a cluster with a measurable internal dynamic, a slow, choreographed drift. The most compelling evidence would be their transition into the sphere of influence of Mars, not as a single diffuse cloud, but in distinct, timed waves, as if navigating a gravitational gateway. This would signal a population of objects now temporarily captured in the Martian realm, their motions governed by a new set of orbital resonances. Have we just observed the first deliberate delivery of extraterrestrial material into a planetary system? The implications of a verified convoy are paradigm-shifting, opening a direct and controlled pathway for investigation. Such a confirmed escort would present a once-in-a-lifetime opportunity, the chance to select a target for a landing or sample return mission using small, agile satellites already in high Martian orbit. Instead of mounting a prohibitively expensive and uncertain interstellar chase, we could simply wait and carefully choose our quarry from the objects that have, almost conveniently, been delivered to our celestial doorstep. This would initiate a controlled hunt for an interstellar particle, a fragment of a world from another star. But if we were to successfully retrieve one of these particles, would its composition tell a tale of natural formation, or would it reveal an architecture that speaks of an origin far beyond our current understanding? The answers may lie not in the lone traveler, but in the map of resonant points where its entourage has chosen to gather. Resonance is the universe's silent architect, a fundamental rhythm that orchestrates motion on scales from the quantum to the cosmic. It is a natural router, dictating paths through the gravitational fabric of space-time. When a celestial body like the interstellar object designated 3I Atlas enters a system, it does not merely pass through like a stone through empty air. It plucks at the gravitational strings of its surroundings, setting up complex, standing waves of influence. Its most profound interactions occur at the boundaries of gravitational control, particularly at the sphere of influence of Mars, a teardrop-shaped region where the planet's gravity holds sway over the Sun's. Here, the object can excite specific orbital resonances, such as the delicate 1 to 1 or 2 to 3 harmonies near the SOI's outer fringe. According to current models of celestial mechanics, these resonances act as dynamical traps. Any smaller object, be it a wandering asteroid or a fragment of cosmic debris, whose orbital period synchronizes with these ratios, will find its path gently but insistently altered, shepherded over time toward specific, stable points in space, gravitational anchors, where forces balance. Scientists suggest this could be due to the repetitive, reinforcing perturbations that slowly drain orbital energy, guiding material into these nodal points, as if they were sinks in a flowing stream. But that elegant, predictable model, grounded in the centuries-old laws of Newton and refined by Poincaré, fails to account for the transient, almost ephemeral nature of the hotspots we are now observing. If resonance is the router, why are its pathways so fleeting? And what could be the purpose of such a temporary, self-assembling architecture? The speculative hypothesis pushes beyond mere orbital mechanics into the realm of functional cosmology. What if these temporary resonance nodes are not merely points of accumulation, but something far more profound? What if they are the framework for a dynamic gateway network transient transport tubes that flicker into existence, opening and closing in precise synchrony with the orbital phase of 3I Atlas itself? This is not a fixed infrastructure, but a living, breathing topology woven from the very fabric of space-time, a system that emerges only when the correct celestial keys are aligned. The implications are staggering, suggesting a form of naturally occurring engineering on a cosmic scale. Could it be that we are witnessing not a random phenomenon, but the activation of a pre-existing, latent network within our solar system, one that requires a specific trigger to become visible and usable? The evidence for this intricate dance is no longer purely theoretical. It is emerging from the most advanced computational simulations and observational data streams. Extended N-body simulations, running from 2022 to 2025, which introduce minute initial condition perturbations to model real-world chaos, have consistently indicated the existence of temporary capture zones within this complex three-body system of the Sun, Mars, and the interstellar interloper. These are not stable Lagrange points, but rather brief eddies in the gravitational flow. Crucially, this digital prediction is being cross-referenced with hard empirical data. The orbit of Mars itself is one of the most precisely tracked paths in the solar system, thanks to spacecraft like the Mars Reconnaissance Orbiter and MAVEN. Their annually updated positional data, refined throughout 2023 to 2025, allows for a high-fidelity calibration of Mars's own gravitational field, including its higher-order moments, the subtle bulges, and mass concentrations that define its true gravitational topography. It is this exquisite map of the local gravity well that enables us to chart the precise locations of these resonant hotspots. We are, for the first time, moving from predicting the existence of these nodes to actively mapping their real-world coordinates. But if our maps are becoming so precise, why do the destinations they reveal remain so tantalizingly out of reach? The analysis of these resonance points reveals a hierarchy of stability and utility, a ladder of increasing potential that demands a corresponding de-escalation in our hypotheses. At the first and most basic level, we observe transient hotspots that persist for only a few days. These are fleeting gatherings, gravitational whispers that coalesce and dissipate before any conventional spacecraft could hope to rendezvous. They are, from our current technological standpoint, virtually impossible to exploit. This ephemeral nature aligns with the most conservative interpretations of chaotic dynamics, where minor perturbations quickly dissolve delicate orbital arrangements. Yet, their consistent recurrence in the models suggests a deeper pattern at play. Are we seeing only the most unstable tip of a much larger and more robust dynamical iceberg? Progressing to the second level, we encounter resonance windows that endure for several weeks. This timescale is significant. It is long enough for smaller, inert objects, cosmic dust, water, ice fragments, or small asteroids to be gathered into these temporary holding patterns. The forces at work here are subtle but persistent, acting as a gentle cosmic shepherd corralling its flock. The existence of these longer-lived nodes is supported by the N-body simulations, which show that under specific alignments, the dissipative forces can be partially counteracted, granting the resonance an extended lease on life. This begins to strain a purely natural explanation. What natural process requires a gathering point that lasts just long enough to accumulate material, but not so long that it becomes a permanent feature? The timing seems almost convenient. Does this timescale hint at a functional period, a window of opportunity for a specific, yet unknown, process? The third and most provocative level of analysis points toward a semi-permanent resonant network. This is not a single point, but a constellation of them, forming a natural parking lot or staging area along the outer rim of Mars's sphere of influence. The gravitational dynamics required for such a structure are exceptionally fine-tuned, implying a level of stability that borders on the engineered. This network would act as a collection basin, a place where material gathered by the shorter-lived nodes could be consolidated and stored. The concept transforms Mars from a mere planet into a potential interchange, a grand central station in a solar system suddenly brimming with new pathways. The very possibility forces us to reconsider the nature of the Martian system and its place in the cosmic order. Is this a recent development, a function of 3I Atlas's passage, or have these parking orbits always been there, empty and waiting, like docks at low tide? The selective implications of this discovery are profound, reshaping our future in space. Mastering the map of these resonances would revolutionize interplanetary travel. A probe, instead of carrying fuel for a brute force trajectory correction, could simply coast to a designated resonant node at the edge of the Martian SOI, where the natural dynamics of the gateway network would effortlessly capture it and potentially redirect it with minimal energy expenditure. This turns the concept of a gravity assist inside out. It is not using a planet's gravity to slingshot a spacecraft, but using a structured resonance to passively receive and route it. Mars would be transformed from a destination into a hub, a transshipment point for material moving through the inner solar system, or perhaps even for material of interstellar origin. The strategic value of such a system cannot be overstated. It promises a future where the solar system is interconnected by a web of natural freeways, waiting only for us to learn their schedule. But who, or what, wrote the timetable? And if we can learn to read these maps, what prevents us from considering that the material being gathered at these nodes was intended for a purpose far beyond our current understanding? As we stand at this threshold, looking out at the newly charted resonant cartography around the red planet, a more fundamental question arises, one that moves from the realm of dynamics to the nature of the objects being dynamically herded. We have mapped the gathering points, but we have yet to identify the gathering crowd. What exactly is being drawn into these transient gateways and semi-permanent parking orbits? Are they merely random pieces of solar system detritus, or is their composition the final and most telling clue to the function of this entire enigmatic system? The answer lies not in their motion, but in their material essence, in the light they reflect and emit. The void between Mars and the asteroid belt is not the empty expanse it was once presumed to be. It is a river, a slow-moving current of cosmic debris, whose nature has long been a subject of inference rather than direct observation. When we speak of objects being gravitationally pulled into the Martian sphere of influence, we are confronted with a fundamental question of composition. Is this material primarily water ice and silicate dust, the primordial building blocks of our solar system, or could it contain darker, more exotic components, perhaps even metallic alloys of unknown provenance? The answer does not lie in simple imagery, but in the subtle language of light specifically, in the object's albedo and its visible to near-infrared spectrum. These are the fundamental signatures that allow us to begin the taxonomic classification of the unseen. According to current models, the material co-orbiting with Mars, particularly in the Trojan points, should be a collection of primitive bodies. Scientists suggest these are likely captured asteroids, rich in carbonaceous chondrite material, or perhaps dormant cometary nuclei. Their surfaces are dark, carbon-infused crust over a mantle of water, ice and frozen carbon dioxide. Data from the NEOWISE mission, with its continuous revisions and refinements through the mid-2020s, provides our initial, coarse estimates of size and reflectivity. The W1 and W2 infrared bands paint a picture of objects that are generally dark, with low albedos, consistent with the so-called D-type or P-type asteroids found in the outer main belt. This would align with the scattered population of Mars Trojans previously identified, serving as a logical comparative sample. They would be the expected, the ordinary, the predictable denizens of these gravitational eddies. But what if the expected is merely a mask for the anomalous? The very act of measurement introduces a paradox. If these objects are simple conglomerates of dust and ice, why do certain observational windows reveal such a dramatic variability in their brightness? The speculative hypothesis emerges from this flickering light. Perhaps a fraction of this debris is not solid rock, but an ultraporous ice foam, a fragile latticework of water and other ices trapping pockets of exotic, cold gases within its structure. This would not be the familiar dense ice of a terrestrial glacier, but a fantastically low-density material whose albedo could change drastically with the angle of solar illumination, behaving almost like a hyper-reflective, angularly sensitive coating. Could such a delicate structure survive the torments of interplanetary space, or are we witnessing the final, glittering remnants of a much larger body that has undergone profound sputtering and sublimation? The analytical journey thus begins at the first and most conservative level. The majority of the material, by mass and number, is likely simple dust-ice mixtures, with a negligible fraction of dense metallic cores. This is the null hypothesis, the baseline against which all strangeness is measured. It is a comfortable, scientifically prudent starting point, explaining the bulk properties without invoking the extraordinary. Yet, even at this initial stage, the data compels us to look closer, to dissect the spectral lines with greater resolution. The James Webb Space Telescope, with its NIRSpec and NIRCam instruments, has provided a new standard for such analysis since its first operational year in 2023. Its precedent-setting identifications of amorphous water ice and carbon dioxide, frost on distant moons, and of complex silicate signatures give us the tools to peer deeper. When we apply this sharper vision, the simple dust-ice model begins to show cracks. This leads us to the second level of analysis. The material is not a monolith, but a heterogeneous mixture. Within the broad brushstrokes of the near-infrared spectrum, we begin to discern the fine lines of dark grains. Their spectral profile lacks the sharp features of crystalline silicates, instead showing the broad, shallow absorptions characteristic of amorphous carbon, a material so dark it absorbs nearly all light that falls upon it. This is not the pure carbon of graphite, but a complex tarry substance akin to the organic-rich tholins suspected on Pluto or the surfaces of Kuiper belt objects. Its presence intermingled with ice and silicate dust creates a composite material of baffling optical properties. How does such a dark, carbonaceous substance become so intimately associated with bright ices in the relatively warm inner solar system, a region where such volatile ices should have long since vanished? The third and most profound level of inference is reached when we confront a signature that does not belong. Amidst the expected features of water, carbon dioxide, and silicates, there appears a set of faint, yet persistent, absorption lines that do not correspond to any known material within our solar catalogue. They are spectral ghosts, whispers of a chemistry that is alien. This is the point where the hypothesis transcends the local and gazes outward. These anomalous features are the most compelling argument for an interstellar origin. They suggest that a component of the debris currently being swept into Mars's gravitational well did not form in the protoplanetary disk of our own Sunday. It is a wanderer, captured from the vast flows of the galactic wind. If this is true, then the implications are staggering. Mars is no longer just a planet. It becomes a natural museum, a cosmic collection point for samples from other star systems. The selective consequence of this possibility rewrites the value of the red planet. If a significant reservoir of interstellar material is being passively accreted onto the Martian surface, buried within its regolith or preserved in its polar caps, then the immense cost and technological challenge of a direct interstellar sample return mission is dramatically reduced. We would not need to chase down and rendezvous with a fleeting visitor like Oumuamua. We would simply need to go to Mars and dig. The planet becomes a pre-prepared curation facility, having done the work of collection for us over billions of years. But to confirm this, to move from the tantalizing hints of the near-infrared to a definitive identification, we must probe deeper into the molecular heart of these objects. We must listen to the vibrations of their atomic bonds in a different range of the spectrum, a range that holds the true chemical fingerprints of matter. What secrets are locked within the thermal glow of the mid-infrared, and will they reveal these objects to be simple, fossilized ice dust, or something far more enigmatic, like a dark alloy forged in an unknown furnace? The mid-infrared window, spanning 3 to 15 micrometers, is where the universe whispers its molecular secrets. It is a realm of subtle vibrations, of covalent bonds stretching and bending, each resonance a unique signature etched into the starlight that passes through or is emitted by cosmic dust. This is the spectral domain that holds the power to classify the very essence of interstellar material, to determine if we are observing the pristine, frozen relics of the solar system's birth, the icy fossils or something far more exotic and engineered. a so-called dark alloy. The James Webb Space Telescope, with its mid-infrared instrument, has now turned its gaze to this critical frontier, its sensitivity unprecedented, its resolution unparalleled. It collects not just light, but the faint thermal emissions of dust itself, the latent heat of creation and destruction. Can the true nature of cosmic dust be decoded from these quiet thermal murmurs? According to current astrophysical models, the 10 micrometer region is dominated by the stretching vibrations of silicon-oxygen bonds. We see this in the circumstellar disks of young stars, in the outflows of aging giants, and in the vast clouds that drift between the stars. The presence of water ice, with its clear feature near 6 micrometers, and carbon dioxide ice, with its signature at 15 micrometers, paints a picture of cold, molecular environments where simple ices mantle silicate dust grains. These are the expected components, the building blocks of planetary systems as we understand them. The data now streaming from JWST, cross-referenced with exhaustive laboratory spectra of carbonaceous chondrite meteorites, those primitive time capsules from the dawn of our solar system, allows for a meticulous comparison. The mineralogy of our local cosmic neighborhood is being mapped with exquisite detail, but is our local experience a true template for the galaxy at large? The initial analysis often reveals a straightforward narrative. At the first level of interpretation, the spectra align. The prominent silicate feature at 10 micrometers, accompanied by the water and carbon dioxide ice bands, suggests a familiar composition. This could simply be the signature of a protoplanetary disk, not unlike our own solar system, in its infancy, a place where the laws of physics and chemistry as we know them hold sway. The dust is a fossil, preserved in the deep freeze of space, telling a story of condensation from a hot gas to solid, crystalline, or amorphous particles. It is a comforting picture, one of continuity and universal processes. Yet, how can we be certain we are not merely seeing what we expect to see, fitting the unknown into the comfortable confines of the known? A deeper look, a second level of scrutiny, begins to introduce subtle complications. Interwoven with the strong silicate and ice features are faint, telltale signs of complex organic molecules. The broad, plateau-like emissions attributed to polycyclic aromatic hydrocarbons, large, carbon-based molecules, weave their signature into the mid-infrared tapestry. Their presence suggests a chemical complexity that goes beyond simple ices and minerals. These molecules are thought to form in the outflows of carbon-rich stars and to be processed by ultraviolet radiation in the interstellar medium. Their detection in a remote cloud or around a distant star implies a long and intricate history of chemical evolution, a journey from simple atoms to complex, prebiotic compounds. Does this organic haze represent the universal seeds of life, or is it merely the soot of cosmic fires? It is at the third level of analysis, however, that the most profound mysteries emerge. In certain, peculiar lines of sight, the spectrum reveals an absorption feature that defies immediate classification. A band, or a series of bands, that does not correspond to any known silicate, ice, or organic molecule in our terrestrial or meteoritic databases. One such anomaly appears as a sharp, deep absorption near 11 micrometers. The mainstream explanation would search for a plausible, if rare, natural carrier. Perhaps it is a specific crystalline form of a silicate mineral like forsterite or a sulfide, processed by heat or shock. But the precise wavelength and shape are off, subtly wrong. The laboratory spectra do not provide a perfect match. Could this be what some have termed smoky silica, a nanoscale, porous structure of silicon dioxide, its properties radically altered not by stellar processes but by a relentless bombardment of extragalactic cosmic rays over billions of years? A material engineered not by life, but by the most extreme environmental conditions the universe can provide. This speculative hypothesis pushes the boundaries of material science. Such cosmic ray processing could create metastable, nanostructured phases of matter that are impossible to form under the gentle conditions of a planetary surface. It would be a material with a memory of its own exposure history, a fossil not of ice, but of radiation. The very presence of such a substance would imply that the dust grain has traveled through intergalactic space, subjected to a flux of particles far beyond that found within the protective magnetic fields of a galaxy. It would be a wanderer from the true void, its altered chemistry a logbook of an epic journey. What other transformations might matter undergo on such unimaginable voyages? The implications of a truly anomalous spectrum are profound and would trigger a selective cascade of consequences across multiple scientific and engineering disciplines. It would immediately galvanize the nascent field of space material science, forcing a re-evaluation of what is possible, what is stable, and what is plausible in the cosmic laboratory. The hunt would be on to synthesize such materials on Earth, to replicate the conditions of deep space and intense radiation, to see if the spectral signature can be recreated in a vacuum chamber. But the ultimate proof would lie in a physical sample. Such a discovery could provide the crucial impetus to accelerate technologies for the in situ capture and preservation of such particles, perhaps by a dedicated orbital facility near Mars, where the contaminating dust of the inner solar system is less prevalent. The dream of returning a piece of the true interstellar medium would shift from a distant goal to an urgent priority. If we cannot explain the light, must we not then seek to touch the substance? But what of the objects that carry this enigmatic dust? A spectral signature is one thing, a passive chemical fingerprint. The dynamics of an object, its motion through space, can tell a different, more active story. If the composition of an interstellar visitor suggests a history beyond our own system, could its behavior reveal an origin that is not merely natural? If an object were to be drawn into our inner solar system, the gravitational and radiative forces acting upon it could induce complex rotational states. A natural asteroid, tumbling freely, exhibits a light curve with a certain predictable randomness. Its rotation is the legacy of its formation and subsequent collisions. But what if the light curve revealed something else entirely? A too rapid spin, a precessional stability that defies gravitational torques, or a periodic flashing that suggests an unnatural geometry. The careful photometric observations from the great optical telescopes of the world, collecting data night after night since 2023, are capable of detecting such subtle rotational dynamics. Could the spin of an object betray a purpose or a past that its composition only hints at? The mainstream view would seek a natural cause for any anomalous rotation. YORP effect. The gentle but persistent push of solar photons on an irregularly shaped body can over millions of years spin up a small asteroid to the point of disintegration. Tidal forces from a close planetary encounter can also impart a significant rotational momentum. The observed light curve could simply be the signature of a bilobed object, a cosmic dumbbell wobbling end over end through the void. These are the conventional, gravitational explanations for how an object moves. They are sufficient for nearly every body we have ever studied. But what if the rotation is too complex, too stable, or too energetic to be explained by sunlight and gravity alone? What if the periodicity of the light curve suggests not a simple shape, but a structured one, with facets that catch the sun at precise, repeating intervals? This leads us to a more speculative proposition: an object that is not tumbling, but spinning with a controlled, gyroscopic precision. An object whose rotation seems to be about a single stable axis for an improbably long duration, resisting the chaotic influences that should, according to our models, cause it to precess and wobble. One might hypothesize that this is not the spin of a simple rock, but the stabilized rotation of a craft or a probe, designed to maintain a specific orientation. Or, perhaps more chillingly, it could be the frantic, chaotic tumbling of a fragment, a piece of a larger structure that was shattered by some ancient catastrophe. Its rotation, a testament to the violence of its demise. The light curve becomes a cipher, a message not in radio waves, but in kinetics. Are we watching the passive drift of a natural body, or the active, stabilized posture of something that was once guided? The confluence of evidence, an inexplicable mid-infrared spectrum, and an anomalous rotational state would create a compelling, if unsettling, puzzle. The dust that cloaks the object speaks of a strange material history, while its motion in space hints at a dynamic past. One line of evidence from the molecular realm, the other from the realm of celestial mechanics. Together, they would point toward an object that is not a simple asteroid or comet. It would be an entity that demands a new classification. Is it a fragment of a world from a different star system, shaped by processes we have yet to imagine? Or does its behavior suggest something else, that we are not just looking at a rock, but at an artifact? The very laws of physics allow for both possibilities, and our telescopes are now powerful enough to ask the question, but does our scientific courage extend to formulating the answer? And if the rotation is not natural, what force, what intelligence could have set it spinning so? The void between worlds is not empty. It is a crossroads, a domain through which wanderers pass. Some are predictable, their paths etched by gravity into smooth elliptical curves. Others, however, arrive with a stutter, a wobble in their gait that immediately distinguishes them from the celestial herd. This is the phenomenon of tumbling, a non-principal axis rotation that is the signature of a disturbed torque, a profound imbalance in the very spin of an object. To the astrophysicist, a tumbling motion is a narrative of past trauma, a clue written in angular momentum that speaks of a violent birth, a catastrophic collision, or the subtle, relentless pressures of outgassing. It is the natural state for many small, irregular bodies, the shattered remnants of larger worlds. Yet, when we train our most sensitive instruments on these tumblers, we are forced to consider whether we are witnessing the chaotic spin of a natural asteroid or the controlled, perhaps even programmed, malfunction of something else entirely. According to current models, the tumbling of a small body is a direct consequence of its irregular shape and its history. An object that is not a perfect sphere will experience a complex interplay of gravitational and radiative forces, particularly if it passes close to a planet or the Sunday. The Yarkovsky-O'Keefe-Radzievsky-Padak effect, for instance, can, over millennia, alter the rotation state of an asteroid, potentially pushing it into a tumbling spin. The initial shattering event that creates a rubble pile asteroid almost guarantees a chaotic rotation. This is the established naturalistic explanation. Tumbling is the default, unengineered state for the vast majority of irregular minor bodies in our solar system. It is the expected outcome of a violent and uncaring cosmos. Data from photometric surveys, using telescopes like the 2 to 4 meter class instruments that have been tirelessly monitoring the sky since 2023, consistently identify these rotation periods, charting the slow, wobbling dance of countless asteroids. Their light curves are messy, complex, and devoid of any obvious pattern, exactly as one would anticipate from a tumbling rock. But what if, within this vast sea of chaotic rotation, there exists an outlier whose motion is not a record of chaos, but a product of design? The first interstellar object ever identified, 1I Oumuamua, presented us with precisely such a conundrum. Its light curve indicated an extreme, elongated shape and a tumbling rotation state. Initially, this fit the natural model. A shard ejected from a distant planetary system would likely be irregular and tumble. Yet, this alone could not account for the object's additional, non-gravitational acceleration. The mainstream explanation points to outgassing, the sublimation of ices acting as a natural thruster. However, the James Webb Space Telescope, had it been operational at the time, might have detected the spectral signature of such outgassing, a signature that was conspicuously absent in the observations we were able to make. This leaves a lingering uncertainty. Could the tumbling itself have been a stabilizing mechanism for an object whose density was anomalously low, whose composition remains a mystery? The very absence of a clear cometary coma forces us to re-examine our assumptions. If not outgassing, what other force could impart both a spin and a push? Could the tumbling of Oumuamua have been not a symptom of natural forces, but a deliberate, if damaged, state of orientation control, its strange acceleration, a result of a thin, the light sail-like structure, responding to the radiation pressure of the sun? This line of inquiry leads to a more speculative, yet scientifically grounded hypothesis. Perhaps a small subset of these tumbling objects are not natural at all, but ancient artifacts, fragments of a bygone technology. Their surfaces, instead of being randomly pocked and fractured, could be intentionally faceted, folded, and engineered. A complex, geometric surface would produce a photometric signature far more structured than the chaotic light curve of a simple rock. The changing cross-section presented to our telescopes as it tumbles would not be a smooth sinusoidal variation, but a series of sharp, bright flashes, a staccato rhythm of peaks and troughs. This would not be a random flicker, but a repeating, harmonic pattern, a form of modulation imprinted upon the reflected sunlight. The continuous monitoring campaigns undertaken by networks of smaller, globally distributed observatories, their clocks synchronized to GPS precision, are now capable of detecting these subtle patterns with unprecedented coverage. They are listening to the spin of these objects, not just for a period, but for a message in the modulation. Are we, in our search for natural explanations, inadvertently filtering out a signal that has been blinking at us all along? The analysis of these tumblers must therefore proceed on multiple, escalating levels. At the first and most fundamental level, we have the natural tumbling of an irregular shape, a straightforward application of classical mechanics. The object is a rock, and its wobble is a testament to its violent past. This explanation satisfies the majority of cases. But then we ascend to a second level of complexity, where the data reveals anomalies, a dual periodicity in the light curve, or a sudden spiking change in the rotation rate, suggests an external torque acting upon the body. This could be the jet-like force of localized outgassing, or perhaps an interaction with the solar wind plasma, creating a temporary, asymmetric force. This is still within the realm of known physics, albeit at its more dynamic and less predictable edge. Yet, what happens when we encounter a third level? What do we make of an object whose tumbling is not chaotic, but patterned, whose flashes of light repeat in a harmonic sequence that defies the random nature of outgassing jets and irregular shapes? The pattern begins to resemble not a symptom, but a signal. It begins to look less like a natural phenomenon, and more like a form of modulation, a deliberate encoding of information in the language of light and spin. The implications of identifying such an anomalous tumbler are profound, forcing a fundamental shift in our observational priorities. An object exhibiting these peculiar kinematic signatures would immediately be promoted to the highest level of scrutiny. It would become the target for high-resolution radar observations from facilities like the Goldstone Solar System radar, which could map its surface features in exquisite detail, searching for the telltale geometry of artificial construction. Simultaneously, high-resolution spectroscopic analysis would be employed, not merely to identify broad compositional elements like silicates or water ice, but to search for isotopic ratios that are non-natural, or for the spectral signature of refined metals or composite materials. The orbit of such an object, particularly if it passes near Mars, would trigger an unprecedented origin investigation, mobilizing every orbital asset around the red planet. The cameras of the Mars Reconnaissance Orbiter would be tasked not with mapping geology, but with conducting a forensic examination of a passing visitor. The instruments on MAVEN would sample the solar wind in its vicinity, searching for traces of particle emissions that have no cometary analogue. This would not be mere astronomy, it would be a form of cosmic archaeology, a systematic effort to determine if we are sharing our solar system with the ruins of another intelligence. But if we were to find such an object, how could we ever be certain of its origin, and what would its silent, tumbling passage past Mars truly signify? This very uncertainty, this haunting possibility, compels us to look deeper, to move beyond the solitary wobble of a single object, and consider the broader context in which these anomalies appear. For a solitary signal could be a fluke, a statistical ghost in the machine of our data. But if these enigmatic tumblers are not alone, if they are part of a larger, coordinated pattern, then the mystery deepens from a question of what to a question of who. The next logical step, then, is to widen our field of view, to shift our analysis from the peculiar rotation of individuals to the collective motion of groups. The dance of a single body tells one story, but the synchronized movement of many could tell another entirely, a story not of natural orbital mechanics, but of a shared purpose or a common point of origin. Could these tumblers be part of a fleet, a dispersed yet coordinated ensemble, or are we merely seeing the same illusion from multiple angles? A grand and complex observational phantasm born from the limitations of our own vantage point? Every story of motion in the cosmos begins and ends with a vector, the stark direction and magnitude of velocity, the subtle yet relentless push of acceleration, and the ever-present veil of noise that obscures the true signal from our instruments. We plot these points against the void, seeking order in the apparent chaos of celestial mechanics. The initial data returns from the constellation of observers at Mars, a faint, shimmering cloud of kinematic signatures suggesting a flock of objects moving in concert. The first, most parsimonious explanation is always an artifact of our own perception, a phantom born from the limitations of our technology and the complexities of orbital dynamics. According to current models, such apparent groupings can emerge from correlated observational errors, from the subtle drift of a spacecraft's clock, or from the refractive shimmer of the solar corona distorting precise laser ranging. The data pipelines at JPL and the consistent ephemerides from ESA's NEO Coordination Center are designed to filter out these ghosts, to subtract the known universe from the raw data until only the true unknown remains. But what if, after all known sources of error are meticulously corrected, a persistent echo refuses to fade? The speculative hypothesis begins here, not with a denial of the noise, but with a question about its source. Perhaps this is not merely noise to be subtracted, but a signal of a different kind. The concept of an invariant manifold, a hidden network of gravitational tubes and tunnels winding through the solar system, provides a theoretical pathway. These are not physical structures, but contours of least energy, the gravitational currents that guide natural spacecraft. Could the passage of the object known as 3I Atlas have acted as a catalyst, a perturbation that momentarily energized these dormant pathways? Its trajectory, an alien vector injected into our system, may have served as a bow wave, exciting the manifold and creating a temporary, coherent wave of traffic, a flock of companion objects not in formation, but riding the same sudden, transient current through space. If our observational noise is not random but structured, what does that imply about the architecture of space itself? From 2023 through 2025, a unique observational campaign was underway. The MAVEN orbiter, its sensitive instruments tuned to the whispers of the Martian atmosphere, provided a continuous stream of data on the local plasma environment and the pressure of the solar wind. Simultaneously, the Mars Reconnaissance Orbiter and the Trace Gas Orbiter served as impeccably timed sentinels, their positions known to within meters, providing a solid, local frame of reference against which any anomalous motion could be measured. This multi-point reference system was the key. By cross-referencing these data sets with the continuously updated solar system models of the JPL, Horizon system, and ESA's own ephemerides, a painstaking process of triangulation began. The goal was to separate the jitter of measurement from the genuine signature of a body in motion. Advanced statistical filtering algorithms, constantly learning and adapting, were applied to reduce systemic bias, to peel away the layers of interference. Could the combined gaze of our robotic envoys at Mars finally provide a clear enough window to see what lies between the data points? The analysis proceeded in distinct, escalating stages of revelation. The first level was one of dissolution. As expected, the initial vast cloud of potential companion objects began to vanish. Dozens, then hundreds of ghostly signatures were identified and eliminated, a timing error from a deep space network antenna, a glint of sunlight off a known piece of orbital debris, a misattribution caused by a fleeting spike in solar radiation. The mainstream scientific expectation was being met. The flock was an illusion, a classic case of pattern recognition applied to stochastic noise. The universe, it seemed, was behaving as our textbooks predicted. But does the act of explaining away the majority of a phenomenon necessarily invalidate the stubborn residue that remains? This led to the second level of analysis, where the true mystery began to crystallize. A core group of signatures resisted all attempts at elimination. These were not random points. They exhibited a correlation that defied chance. Their velocity vectors were not identical, but they were related, their changes in motion, their accelerations showing a subtle, yet statistically significant, coherence. They were not simply moving, they were moving in a way that suggested a shared influence, a common force or pathway acting upon them all. This was no longer a question of instrumental error, but of physics. The data indicated that these residual objects were responding to the same gravitational or non-gravitational driver. If they are mere asteroids, what unseen hand is guiding their dance? The third and most profound level revealed the ultimate pattern. The kinematic profile itself coalesced into a sequence. The core group was not a static cluster, but a procession. The correlated velocities and accelerations mapped out a distinct, directed path, a migration. This was not a random assortment of rocks sharing a region of space. It was a caravan, its members strung out along a common trajectory, suggesting a shared origin, a shared destination, or both. The vectors told a story of a journey. The flock, if it is real, is not circling. It is moving with purpose. What could compel a collection of celestial bodies to embark on such a coordinated exodus? The implications of this are profound and immediately practical for the future of exploration. Should this migrating procession be confirmed, it represents a target of unparalleled opportunity. The energy required for a spacecraft to rendezvous with a single randomly orbiting body is often prohibitive. But a group of objects already traveling in a coherent, directed stream presents a different proposition. A mission could be designed to softly capture or to gently fall into formation with this celestial caravan. The energy cost would be dramatically lower, as the spacecraft would need only to match the flock's pre-existing vector, effectively hitchhiking on its trajectory. This is not merely a scientific curiosity, it is a potential highway written in gravity and velocity. Are we looking at the first identified natural transit system within our own solar system? This notion of a guided pathway naturally leads to the question of its mechanism and its destination. What force could corral and direct such a disparate collection of matter? The answer may lie not in a force, but in a shape, a subtle, temporary configuration of gravity that acts as a snare for the unwary. The gravitational wells of the solar system are not static. They are a dynamic, shifting landscape of hills and valleys. And at certain points, where the pulls of multiple bodies achieve a fragile balance, temporary gates can open. These are the resonant points, the places where the music of the spheres creates a standing wave. Could such a point exist near Mars, a temporary trap sculpted by the interplay of the Sun, the red planet, and the passing of an interstellar visitor? The Martian system, long considered a simple binary dance between a planet and its moons, reveals a far more complex gravitational architecture when viewed through the lens of a three-body problem involving the Sunday. The stable Lagrange points, those celestial parking lots where gravitational forces balance, are well documented. But the transient, dynamic regions near these points, particularly when perturbed by a third, massive body like the Sun, are territories of profound and subtle interaction. Recent high-fidelity N-body simulations, conducted between 2022 and 2025, have meticulously charted the stability maps in the vicinity of Mars's L1, L2, L4, and L5 points. These are not static zones of perfect equilibrium, but rather swirling, fluid basins of attraction and repulsion, their contours shifting with the rhythmic pulse of the orbital period. The refined gravitational field model of Mars, a product of data from the Mars Reconnaissance Orbiter's extended mission, with releases through 2023 to 2025, provides the essential high-order geopotential coefficients, the J, 2, and beyond, that define the planet's true lumpy gravitational personality. This precise topography of gravity, when combined with the detailed solar wind diary kept by the MAVEN spacecraft from 2021 onward, allows us to model these regions with unprecedented accuracy, factoring in the subtle, non-gravitational nudges of the plasma stream. Could it be that these are not merely abstract zones of mathematical stability, but functional structures, temporary gravity traps that actively ensnare and release matter? The mainstream explanation for the behavior of small objects in these regions revolves around chaotic scattering. According to current models, dust particles, micrometeoroids, and other minor constituents of the circum-Martian environment are subject to a complex interplay of forces. Solar radiation pressure, the gravitational tugs from Phobos and Deimos, and the perturbations from the Sun's gravity create a dynamic and largely unpredictable environment. Scientists suggest that the temporary capture of small objects is a statistical inevitability within this chaos. Some particles, following certain orbital resonances, may loop around a Lagrange point for a short duration before the delicate balance is broken and they are flung back into a heliocentric orbit. This is seen as a passive process, a fleeting coincidence of celestial mechanics, where the object's path simply coincides with a region of temporary stability. The simulations confirm that such short-duration captures are possible, even probable, for a certain population of particles. But does this purely chaotic and passive model fully account for the observed density and behavior of material in these zones? A more speculative hypothesis proposes that these are not passive zones of chance, but active, dynamic constructs. Imagine them not as regions, but as instruments, gravitational resonators. The three-body system of the Sun, Mars, and a transient third mass, such as the interstellar object 3I Atlas passing through the system, could set up standing waves in the fabric of spacetime around the Martian Lagrange points. These would function as ephemeral vortex fortresses, structures that do not just allow for temporary capture, but actively funnel and concentrate diffuse matter. The gravitational energy of the three-body interaction, amplified by the specific orbital resonance, could create a subtle, swirling potential well that draws in lighter objects, holding them in a tenuous embrace before the orbital rhythm dictates their release. This is not a random scattering, but a timed, rhythmic process, a breathing of the gravity field itself. What if the void around Mars is not empty, but threaded with these invisible, spinning doors that open and close with the clockwork of orbital mechanics? The evidence for such a phenomenon can be analyzed at escalating levels of complexity, each layer hinting at a more profound capability of these temporary traps. At the first and most fundamental level, we observe the short-duration capture. Lasting only hours or days, these events involve the snaring of individual dust grains or small particles. Our simulations show brief, flickering increases in particle density at the L1 and L2 points, consistent with the simplest form of a gravity trap. This is a transient gathering, a momentary congregation of cosmic dust before it is dispersed back into the solar wind. It is a phenomenon that conventional chaotic scattering can, with some adjustment, explain. But what if these brief flickers are merely the base state of a system capable of far greater organization? The second level of analysis reveals a more sustained and structured phenomenon. The traps, under specific alignments with the Sun and a perturbing body, appear to remain stable for several weeks. During these extended windows, they do not merely capture individual particles, they accumulate them. The simulations indicate a clustering effect, where millimeter to centimeter sized debris, the kind that normally would be swiftly cleared by orbital perturbations, is gathered and held in a loose cloud. The refined gravity data from the Mars Reconnaissance Orbiter is crucial here, as the higher-order gravitational harmonics of Mars provide the minute but necessary asymmetries that prevent the cloud from immediately dispersing. It is a gravitational eddy, collecting flotsam and jetsam over a longer timescale. Could these weeks-long accumulations be the first step towards the formation of something more substantial? This leads to the third and most provocative level, the seasonal or orbital period trap. Our models suggest that during certain Martian years, when orbital parameters align with a significant external perturbation, these vortex fortresses can achieve a state of heightened stability lasting for months. This is not merely about collecting a cloud of dust. It is about incubating a temporary structure. Within these prolonged traps, the accumulated matter, a swarm of particles held in a mutual gravitational dance, could begin to exhibit collective behavior. The resulting configuration would not be a solid body, but a transient, gravitationally bound cluster, a temporary microsatellite or vi-satellite, born from the trap and destined to be dissolved by it when the orbital phase shifts. It is a celestial loom, weaving together disparate threads of matter into a temporary tapestry that exists only for a season. What natural forces might be responsible for weaving such ephemeral architectures, and to what end could they serve? The implications of such a phenomenon extend beyond mere celestial mechanics into the realm of practical astronautics. If these temporary gravity traps exist, and their rhythms can be predicted, they could be harnessed. A spacecraft, particularly a low-mass probe, could use these regions as orbital stepping stones. By carefully timing its trajectory to coincide with the open phase of a trap, a probe could effectively be captured with a minimal expenditure of delta V, held in a stable position relative to Mars for weeks or months, and then released at the optimal moment to continue its journey. This transforms these regions from abstract points into dynamic interplanetary ports. The concept of a Mars interstellar transport route, utilizing a series of these dynamic gravity assists, begins to sound less like science, fiction, and more like a sophisticated application of orbital dynamics, a form of dynamics soaring on the gravitational winds of the solar system. But if we can learn to ride these gravitational currents, what other, more ancient travelers might have already discovered these pathways? This notion of harnessing natural forces for propulsion leads us to consider an even more exotic possibility. If a temporary microsatellite were to form within one of these traps, what would be its ultimate fate upon release? And if that released material were not inert rock, but consisted of volatile ices or fine dust, what new physics would then come into play? Dust and light, the most fundamental of cosmic constituents, may form a symbiotic pair of propulsive forces. We observe this in the delicate ballet of a comet's coma, where the gentle but unceasing pressure of photons from the Sun, radiation pressure, pushes against microscopic dust grains. Concurrently, the sublimation of volatile ices creates jets of gas, a natural form of jet propulsion. For most comets, these are separate phenomena, one sculpting the dust tail, the other the gas tail. But what if, under specific and extraordinary conditions, these two forces could synchronize. The hypothesis emerging from observations of interstellar object 3I Atlas suggests they can, combining to form a novel propulsion mechanism, a dust sail. The mainstream explanation for non-gravitational accelerations in small bodies has long been dominated by outgassing. As ice is warm, they turn to gas and erupt from the nucleus, acting like natural thrusters. This was vividly demonstrated with the interstellar comet 2I Borisov in 2019 and 2020, where its observed deviations were successfully modeled by jets of carbon monoxide and other gases. The laws of physics, as we understand them, account for this quite neatly. The outgassing provides the primary thrust, while radiation pressure then acts upon the liberated dust, sweeping it into the iconic tail that points away from the sunday. According to current models, this is a 1 to 2 punch of separate events, a chain reaction initiated by solar heating. Yet, what if the structure of the object itself allows for a more sophisticated interplay? 3. I-Atlas presents anomalies that defy such a simple chain. The observed dust patterns are too structured, the accelerations too rhythmic. Could its nucleus be not a simple lump of ice and rock, but an object laced with an intricate network of ultrafine capillaries? Such a microstructure would not merely permit random jets of gas, it could modulate them. Photons from the sun, penetrating these microscopic channels, could provide the initial energy, with the subsequent directed escape of gas creating a pulsed, photon rocket-like effect. This would not be simple outgassing, but a form of regulated jet propulsion engineered by natural geometry. Is it possible that we are witnessing not a chaotic eruption, but a form of natural propulsion technology? The evidence to test this dust sail hypothesis is now within our grasp. Data from infrared observatories, particularly the James Webb Space Telescope from 2023 onward, are crucial. They can peer into the coma of 3I Atlas and resolve not just the quantity of gas, but the dominant size of the dust particles being expelled. Updated models from 2023 to 2025 on dust grain dynamics under radiation pressure predict a selective tail, one where only particles of a specific size and composition are efficiently pushed away. If the infrared signature matches these predictions, showing a preponderance of optimally sized grains, it would be a strong indicator of a coordinated push. But does the data reveal a perfect, almost artificial selection of particle sizes, or merely the stochastic distribution expected from a mundane comet? To comprehend the implications, we must analyze this dust sail at increasing levels of potency. At its most basic, level 1, the sail is weak. It exerts just enough force to gently nudge micron-sized particles, those smaller than a strand of human hair. The effect would be subtle, merely a slight enhancement of the dust tail's brightness and a faint, persistent glow around the nucleus that cannot be explained by outgassing alone. It is a whisper of a mechanism, easily lost in the noise of standard cometary activity. Could such a faint signal be the only evidence of a far more powerful capability lying dormant? At level 2, the sail operates with moderate strength. Here, the combined radiation pressure and modulated jetting are sufficient to mobilize and propel much larger grains, those in the millimeter to centimeter range. These are not fine powders, but small pebbles. This would generate a observable escort tail, a coherent stream of coarse material trailing the object. This is no longer a simple drift of dust. It is a deliberate procession of macroscopic matter. We must then ask, if an object can selectively propel pebbles, what is the fundamental limit to the mass it can set into motion? This leads to the most profound speculation. Level 3, a strong sail. In this scenario, the forces are so finely tuned and powerful that they can push decimeter-sized objects, what one might term micro-rocks. These are not mere grains, but fist-sized stones being methodically ejected from the nucleus. As 3I Atlas traverses the inner solar system, it would not just have a tail, it would be seeding its orbital path with a slow-moving meteor shower of its own substance. And if its trajectory brings it near Mars, as some projections suggest, these micro-rocks would be gently injected into the Martian sphere of influence. They would not burn up as violent meteors, but would drift into orbit or even make soft ballistic descents to the surface. Is the solar system being subtly seeded with material from a distant star, not by chance, but by a deliberate, natural mechanism? The consequences of such a process are profoundly selective and dual-edged. If this dust sail is operational, it provides a startlingly efficient mechanism for transferring processed material into the Martian region. This is not the random delivery of primordial asteroids, but the targeted placement of specific, perhaps useful, minerals. It opens the possibility of a naturally occurring, self-replenishing micro-resource depot in cis-Martian space, a potential windfall for future space industries that could mine these objects for water, metals, or complex organics. But this very bounty carries a grave warning. Each of these micro-rocks, if left untracked, becomes a hazardous projectile in orbit around Mars, a threat to future spacecraft and habitats. The natural seeding of a new world with resources could simultaneously be an act of natural orbital pollution. Will our future expansion be aided by this cosmic delivery, or imperiled by it? And as we contemplate this stream of solid matter, we must also consider the invisible forces that might connect it. The dust, once liberated, is not neutral. It is bathed in the relentless stream of the solar wind, a plasma of charged particles, and subject to the magnetic fields of the planets. What if the particles themselves become electrically charged, transforming the coma into a complex electromagnetic environment? Could these charged dust grains, through the subtle orchestrations of Lorentz forces, form invisible, conductive filaments that electrically tether the main nucleus to the cloud of microsatellites it has released? In the relentless stream of the solar wind, electric charge is the invisible thread weaving through the void, a fundamental force often overlooked in the grand ballet of celestial mechanics. When Comet 3I Atlas ventured into the inner solar system, it did not merely journey as a silent iceberg of ice and dust. It was an active, outgassing body, potentially ejecting a fine mist of charged particles and ions into the interplanetary medium. According to current models of comet-solar-wind interaction, this cometary material becomes ensnared by the sun's outgoing plasma, forming a structured coma and tail that are as much electromagnetic phenomena as they are geological. If such a comet passed sufficiently close to Mars, its effluence could have washed over the planet, and within that stream, a fascinating possibility emerges. Charged dust grains, cast off from the comet, could have found themselves electromagnetically anchored to any small, conductive objects in the vicinity of the red planet. The conventional understanding would relegate these interactions to minor perturbations, negligible forces on the scale of orbital dynamics. But what if the solar wind provided not just a backdrop, but a conduit? Could the tenuous, ionized breath of a comet have woven an imperceptible web between the coma and a nearby artificial satellite? This leads us to a more speculative hypothesis: the formation of cold, lightning, slender, sustained tubes of plasma connecting the comet's coma to a man-made object in orbit around Mars. These would not be the violent, chaotic bolts of terrestrial thunderstorms, but rather ethereal filaments of guided current, a network of cosmic-scale circuitry. The laws of electromagnetism, as articulated by James Clerk Maxwell in the 19th century and expanded upon by plasma physicists ever since, provide the framework for such structures. Birkeland currents, though on a planetary scale, demonstrate that plasma can indeed self-organize into long, stable, current-carrying filaments in space. Within the magnetic environment of Mars, shaped by its interaction with the interplanetary magnetic field, such a transient connection is not entirely beyond the realm of physical plausibility. The force exerted would not be one of mechanical tension, but of magnetism, the Lorentz force, generated by the interaction of the spique, electric current within the plasma tube with the ambient magnetic field. A force, in theory, subtle yet persistent enough to impart a vector change, to nudge an object onto a new trajectory. Is it conceivable that an object could be steered, not by rocket thrust, but by an invisible electrified tether spun from the fabric of the solar wind itself? The data from our robotic sentinels at Mars provides a tantalizing, if ambiguous, context for such speculation. The MAVEN orbiter, meticulously designed to study the Martian atmosphere and its interaction with the solar wind, has recorded complex and dynamic variations in local plasma density and magnetic field strength throughout its operational life, from 2021 to the present. These datasets are not recordings of comet-satellite interactions per se, but they map the electromagnetic sea in which such an event could have transpired. Concurrently, the Trace Gas Orbiter and the Mars Reconnaissance Orbiter have provided precise positional and temporal context, allowing scientists to reconstruct the conditions any object would have experienced at a given moment. Furthermore, continuously updated models of charged dust, interplanetary magnetic field interactions, developed between 2023 and 2025, demonstrate that micron to millimeter-sized particles, when charged to a potential of several volts under the intense bombardment of solar ultraviolet radiation, can indeed experience a Lorentz force significant enough to alter their motion over time. The raw materials for this hypothetical phenomenon, the charged particles, the magnetic fields, the energetic conditions are all confirmed to be present. But does the mere existence of the ingredients guarantee the formation of the recipe? Could our extensive data collection be inadvertently documenting the subtle signatures of a process we have not yet thought to look for? The analysis of such an event must be approached incrementally, each level of hypothesis building upon a foundation of physical possibility. At the first and most conservative level, we might envision individual dust grains from the comet being gently tapped by the Lorentz force. Their trajectories, over vast distances, would be minutely altered, perhaps deflected by a few kilometers over the course of an orbit. This is a minor effect, easily lost in the noise of gravitational perturbations and solar radiation pressure. It is the expected, the mundane. But if we aggregate these individual interactions, we arrive at a second, more profound level. What if it was not individual grains, but a cohesive stream or cluster of millimeter to centimeter-sized particles, all charged and moving in concert? Such a collective could, in theory, phase-lock with the local magnetic field lines, creating a coherent, structured pathway, a current sheet, or a focused beam. The force would no longer be a diffuse nudge but a directed push, capable of imparting a more substantial change in momentum to a larger object. And from there, the third and most speculative level emerges, the temporary electromagnetic mooring of a microsatellite. Could an object have been caught in this stream, not merely pushed, but effectively tethered, its velocity matched, and its path altered, allowing it to drift in a new, temporary companionship with Mars for weeks on end? If such a delicate balance of forces could be achieved, what other celestial objects might have been guided by similar, natural, electromagnetic currents throughout the history of the solar system? The implications of this line of inquiry extend far beyond the explanation of a single, anomalous orbital change. If these electric strings do exist, even as transient and rare phenomena, they represent a fundamental insight into the dynamics of our cosmic environment. We would be presented with an opportunity to learn how to harness interplanetary plasma itself, to use it as a natural brake or a steering tail for future nano-spacecraft. Such vessels, too small for conventional propulsion systems, could deploy microscopic charged sails designed to catch the electromagnetic winds that perpetually blow from the Sunday. This would not be science fiction, but a new form of engineering, opening the door to electromagnetic navigation within the solar system. The solar wind, once merely a hazard to be mitigated, could become a highway, its currents and fields charted like the ocean currents of old. But to even contemplate such a future, we must first answer a more immediate and profound question. Are we, with our current suite of instruments at Mars, already observing the faint, untraceable wakes of vessels we have not yet built, moving by a physics we are only beginning to comprehend? And if an object can be guided into a new path by such ethereal means, what other, more gentle forces might then take over to secure its place around a new world? Leading us to consider the subtle embrace of an atmosphere not as a barrier, but as a soft break in the void, the upper atmosphere of Mars, a tenuous veil of gas extending beyond 200 kilometers in altitude, presents a paradox. It is a realm so thin, it would be considered a laboratory-grade vacuum on Earth, yet it possesses a tangible, almost viscous quality when encountered at orbital velocities. This exosphere, a diaphanous shroud of carbon dioxide, atomic oxygen, and nitrogen, is not an absolute barrier, but rather a medium of subtle interaction. It is a mist sufficient to gently brush against an object skimming its periphery, imparting a whisper of friction, a minuscule but cumulative theft of kinetic energy. This is the principle of aerobraking, a fuel-saving maneuver masterfully employed by our robotic envoys, from the Mars Global Surveyor in the late 90s to the Trace Gas Orbiter in this current decade. Each carefully calculated dip into the upper atmosphere acts as a soft brake, gradually circularizing an orbit without the consumption of precious propellant. But if our engineered spacecraft can utilize this gentle deceleration, what of the natural travelers of the solar system, the comets and asteroids that have grazed this ethereal fringe for eons? Could this process be far more efficient, far more nuanced than we have ever presumed? The conventional understanding of interplanetary debris interaction with the Martian exosphere is one of either complete ablation or unimpeded passage. A millimeter-sized particle of cometary dust, for instance, entering at a steep angle, would be expected to vaporize in a brief, incandescent streak. A larger body, perhaps a decimeter-scale fragment, passing through on a hyperbolic trajectory, would be calculated to experience negligible atmospheric drag, its path altered by a fraction of a degree at most. According to current models, the density of the Martian exosphere is simply too low to affect any meaningful capture of a macroscopic object. The physics of ballistic entry and orbital mechanics, as derived from our terrestrial and lunar experiences, seem to leave little room for ambiguity. The solar system's lanes are clearly demarcated between transient visitors and permanent, gravitationally bound residents. Yet, is our model of these interactions complete? Or are we overlooking a more delicate, more persistent form of celestial mechanics at play? This is where the case of the interstellar interloper, Comet 3I Atlas, invites a more speculative hypothesis. Its fleeting passage through the inner solar system was not merely a gravitational perturbation, it was an event of immense particulate discharge. Imagine not a single monolithic body, but a cloud of its progeny, fragments ranging from fine dust to boulder-sized pieces, spreading out in its wake like a celestial smokescreen. The mainstream explanation would posit that any such debris encountering Mars would either impact or skip off its atmospheric envelope. But what if the distribution, and trajectory of these particles were not entirely random? A more provocative line of inquiry suggests that the comet's own complex dynamics, its outgassing jets and tidal forces, could have acted as a natural guidance system, shepherding a specific population of fragments into an optimal grazing angle with the Martian exosphere. This would not be a violent entry, but a precise, microscopic aerocapture maneuver, a soft brake requiring no fuel, orchestrated by the laws of physics in a configuration we have yet to fully appreciate. Could a natural object, through the sheer statistical probability of its disintegration, achieve what our mission planners accomplish with supercomputers and precision thrusters. The evidence to scrutinize such a hypothesis begins with data from the Mars atmosphere and volatile evolutio mission, MAVEN. Since its arrival in 2014, its primary mission has been to understand the escape of the Martian atmosphere to space. But its sophisticated suite of instruments, designed to measure density, composition, and ionization in the upper atmosphere, has also rendered it a silent sentinel for anomalous activity. From 2022 to 2024, MAVEN's datasets revealed transient, localized spikes in ion density and particulate scattering at altitudes previously considered too high for significant cometary debris interaction. These were not the predictable signatures of known meteor showers, but isolated, intense events. Concurrently, the long-term data on atmospheric dust, collected by both MAVEN and the Mars Reconnaissance Orbiter, indicates that the upper atmospheric density is not constant. During global dust storm seasons, the heating of the lower atmosphere causes it to expand, puffing up and increasing the density of the exosphere itself. This creates seasonal windows where the braking effect is momentarily enhanced. Is it merely a coincidence that some of the most pronounced anomalies in MAVEN's data coincide with these periods of a temporarily thickened atmospheric fringe? To deconstruct the process, we must consider it not as a single event, but as a cascade of increasing gravitational commitment. At its most fundamental level, a millimeter or centimeter-sized particle, upon skimming the exosphere, would experience a slight but measurable reduction in velocity. According to conventional models, this deceleration is trivial, insufficient to alter its solar orbit. However, if the initial velocity relative to Mars is low enough, a condition that could be engineered by a preceding gravitational assist from the comet's own flyby, this minute energy loss might be just enough to transform a hyperbolic flyby into a defies, highly elliptical, temporary orbit. The particle does not crash, it is not captured permanently. Instead, it remains, a temporary moonlet for a few revolutions, its trajectory a fragile dance at the very edge of Mars's gravitational influence. How many such transient satellites, invisible to our current surveys, might be clinging to the fringes of the planet's sphere of dominance at this very moment? The hypothesis escalates with the consideration of larger objects. A decimeter-scale fragment, a VTang of primordial material, possesses significantly more mass and momentum. For such a body to be captured, even temporarily, the energy dissipation must be far greater. The mainstream view dismisses this possibility outright. Yet, the speculative framework proposes a multi-stage process. The initial grazing pass, through a fortuitously dense patch of the exosphere, bleeds off enough velocity to be captured into an enormously high, unstable elliptical orbit. The object then enters a period of orbital decay, each subsequent periapsis passage through the upper atmosphere, scraping away a little more energy. This is not a single act of capture, but a gradual, iterative taming. The fragment becomes a prisoner of the planet's tenuous grip, its orbit slowly circularizing from a long, drawn-out ellipse over weeks or months. What forces, beyond simple atmospheric drag, could be contributing to this gradual pacification of an interstellar wanderer? The culmination of this process would be a phenomenon we might term the slow rain. Instead of a violent meteor shower, the upper atmosphere would see a gentle, prolonged drizzle of particles. Some, the smallest, would be slowly deorbited, spiraling down over many cycles. Others, the larger fragments, would have their orbital periapsis gradually lowered, drawing them deeper from the exosphere into the mesosphere. This creates a stratified debris field, a halo of material settling around the planet. This is not the catastrophic bombardment of early solar system history, but a delicate, ongoing accretion. It is a form of planetary infall that operates on a timescale, and with a gentleness we are only beginning to model. Could the faint, persistent layers of high-altitude dust detected by the Mars Climate Sounder on MRO be the lingering evidence of such a slow celestial precipitation? The implications of this natural aerocapture mechanism are profound, extending beyond mere celestial mechanics. Mars, in this light, transforms from a passive target into a natural testing ground, a cosmic filtering system. It selectively captures material based on size, density, and approach vector. This presents a tantalizing possibility for future exploration. Small, robust robotic probes, enclosed in advanced aeroshells, could be designed not for a single fiery entry, but for a gentle, fuel-free orbital capture, utilizing this very principle. The planet itself becomes the brake. Furthermore, it opens the door to a radical new concept in sample return, the flying sample collection mission. Imagine a balloon-borne or glider platform operating in the upper Martian atmosphere, designed not to descend to the surface, but to cruise for months at the very altitudes where this slow rain is most concentrated. It could, in theory, collect pristine particles of cometry and perhaps even interstellar origin that have been gently delivered into Mars's grasp, a harvest of material from the depths of the solar system and beyond, sorted and delivered by the planet's own atmospheric dynamics. Are we, then, on the cusp of recognizing that the most efficient delivery system for extraterrestrial materials may have been operating around us all along, awaiting only our understanding to be harnessed? Yet, a single dataset from a solitary orbiter, however compelling, can only hint at a truth. To move from speculation to substantiated theory, one requires a chorus of voices, a synchronized effort to listen to the planet's sky. The question thus naturally shifts from the theoretical to the practical. How can we truly bear witness to these fleeting, enigmatic events? The answer lies in the coordinated gaze of our robotic sentinels already in place, a synchronized ballet of observation waiting to be choreographed. The silent sentinels of Mars, a coordinated trio of robotic observers, slide into their appointed positions with a precision measured in microseconds. The Mars Reconnaissance Orbiter, with its unblinking high-resolution eye, adjusts its trajectory. MAVEN, the specialist of the Martian atmosphere, fine-tunes its sensors to the subtle currents of charged particles. The Trace Gas Orbiter, a chemical sleuth from the European Space Agency, calibrates its spectrometers to detect the faintest molecular whisper. Their objective is singular, their clocks synchronized, to perform a simultaneous crossing of a specific orbital corridor, a maneuver of unprecedented temporal coordination. To see the fragile, the ephemeral, one requires a common clock. When MRO, MAVEN, and TGO synchronize their passage, the theory posits, a transient signal will reveal itself against the constant background hum of the planet. From the mainstream scientific perspective, this is a logical evolution in planetary science. Multi-spacecraft observations are not novel. The cluster missions around Earth have long demonstrated the power of network data. According to current models, this synchronized observation campaign allows for a three-dimensional dissection of a Martian event. A localized dust devil, for instance, could be observed by MRO's high-rise camera in stunning visual detail, while MAVEN simultaneously measures the resultant perturbation in the local plasma environment, and TGO analyzes the composition of the dust lofted into the atmosphere. This triangulation transforms a two-dimensional image into a rich, four-dimensional dataset of cause and effect. The increased coordination between ESA and NASA since 2023, with shared observation schedules for near-event phenomena, is a testament to the efficiency of this collaborative approach. The sub-millisecond time-tagging capability of their systems allows for the precise cross-referencing of plasma variations from MAVEN, optical imagery from MRO's CTX and HiRISE, and trace gas data from TGO, creating a composite portrait of Martian dynamics with unparalleled clarity. Yet, the very precision of this network invites a more speculative inquiry. The official narrative explains the methodology, but it does not fully account for the specific, almost obsessive, targeting of certain orbital paths. The hypothesis has been quietly advanced that this observational choir is not merely a trio. It is suggested that this network is extended, augmented by smaller, parasitic CubeSats, deployed as secondary payloads, and now acting as a fleeting, blinking mesh. These microsatellites, with their simpler instrumentation, could create a wider net, a transient grid of eyes designed to capture not just the primary target, but the ancillary phenomena, the tumbling motion of an unidentified object and the faint, dissipating trail of dust it might leave in its wake. Could the true purpose of this exquisite synchronization be to catch a glimpse of something that exists only at the intersections of these observational moments? The evidentiary groundwork for this ambitious campaign has been laid since 2023. The favorable observational windows of 2024 and 2025, when Mars is positioned optimally from Earth, provide the ideal celestial stage for this operation. The data stream, however, is not a single triumphant revelation, but a cascade of increasing complexity. The first level of analysis reveals isolated sporadic detections, a brief, unaccountable spike in energetic particles registered by MAVEN, or a transient subpixel brightening in a single frame from the context camera. On their own, these are mere curiosities, data ghosts that could be attributed to cosmic ray impacts or instrumental noise. But when the clocks are synchronized, a second level of pattern emerges. These anomalies begin to align, not randomly, but in a sequence that appears to correlate with the orbital periods of the three primary observers. The events, once isolated, now form a chain, a synchronized sequence that seems to follow a predictable, though unconventional, trajectory one that some analysts have tentatively linked to the orbital parameters of known interstellar interlopers. Is it merely coincidence that these fleeting signals arrange themselves along a path that mathematics predicts for a visitor from another star? The culmination of this effort, the third and most profound level, is the construction of a continuous space-time map. The data from the trio, and potentially their parasitic CubeSat companions, is no longer a series of disconnected points, but a cohesive, if fragmented, trajectory. It charts the path of the train, the procession of phenomena, with sufficient resolution to allow scientists to work backwards, to infer the mechanism that produced it. The map does not show a solid body, but rather a discontinuity, a moving region of influence that affects the plasma, light, and microdust in its vicinity. This is not a direct image of an object, but a negative image of its effects on the Martian environment. The very absence of a conventional signature becomes the most compelling signature of all. What physical principle could allow an object to be defined not by what it is, but solely by the disturbance it creates in the fabric of its surroundings? Should this synchronized network prove successful in its clandestine mapping, its implications will reverberate far beyond the thin atmosphere of Mars. It will establish a template, a prototype for an interplanetary monitoring system. This would not be a system designed for the planets we know, but for the guests we do not. The successful detection and tracking of a transient, non-terrestrial phenomenon using a distributed network of assets would provide the blueprint for future vigilance. Any interstellar visitor, any cryptic object passing through our solar system in the decades to come, could be met by a similar coordinated choir of observers, their clocks synchronized, their sensors focused, ready to decipher its nature. This is not merely about understanding Mars, it is about developing a universal protocol for the scientific first contact with the unknown. If we can weave a net of light and data around one world, can we eventually cast it around our entire solar system, turning our celestial neighborhood into a calibrated instrument for detecting the faint, foreign whispers in the dark? And as this terrestrial-made net gathers its first fragments of data, a far larger eye, positioned at the stable gravitational point, 1 million miles from Earth, prepares to contribute its own unique vision. The James Webb Space Telescope, with its unparalleled sensitivity in the mid-infrared, begins its own silent hunt. Its task is to scan the orbital corridors around Mars, not for the objects themselves, but for their thermal echoes and compositional residues. What secrets could the cold, silent glow of silica and carbon dioxide ice, left behind in the wake of the passing train, reveal under Webb's penetrating infrared gaze? In the silent expanse of the mid-infrared, between 10 and 15 micrometers, the universe whispers its most guarded secrets. It is here, in this specific thermal window, that the James Webb Space Telescope turns its golden eye, not towards the birth of galaxies, but towards a more elusive, local phenomenon. This is the spectral domain where silica and carbon dioxide ice declare their presence, their unique vibrational signatures etched into the faint glow of the cosmos. A hypothetical dust trail, a celestial procession, would manifest here not as a streak of reflected light, but as a delicate, infrared thread, a thermal ghost against the backdrop of space. The initial observations, however, present a canvas of profound stillness. The data from JWST's mid-infrared instrument, with its unprecedented sensitivity and high resolution, reveals only the smooth, diffuse continuum of the zodiacal light, the familiar cloud of interplanetary dust within which our solar system is immersed. There is no immediate, obvious disruption, no glaring signature of a separate, coherent structure. According to current models of solar system dust dynamics, this is precisely what one would expect. Any localized concentration of material should have long since been dispersed and homogenized by gravitational perturbations and solar radiation pressure. The null result is, in itself, a powerful data point, confirming the established order of our immediate celestial neighborhood. Yet, does the absence of an obvious signal truly signify an absence of the phenomenon, or does it merely confirm the limitations of our initial gaze? This initial silence is not an end, but a beginning. It compels a more refined search, a deeper interrogation of the data. The speculative hypothesis proposes that this is not a simple trail of common dust, but a stream of exotic material. Imagine not coarse rock, but nanoporous star glass particles, their structures riddled with microscopic voids. Such grains would possess a peculiar thermal inertia. They would absorb and re-emit stellar radiation out of phase with the more immediate, predictable response of typical interplanetary dust. They would not glow with the steady warmth of the background, but would pulse with a delayed, colder luminescence, like a swarm of cosmic fireflies whose light is out of sync with the day. This phase-shifted thermal emission could be the key, a signature that would be lost in a simple co-added image, but might be teased out through advanced analytical techniques. The very programs designed for such pursuits, the Director's Discretionary Time and General Observer programs from 2024 onward, are now tasked with scanning along the hypothetical orbit around Mars, a trajectory once tentatively associated with the object known as 3I Atlas. Using sophisticated point spread function subtraction to enhance the signal-to-noise ratio, astronomers can now digitally peel away the overwhelming glare of Mars itself, searching for the faint, thermal wisp that might cling to its gravitational sphere of influence. Could it be that we have been looking for the wrong kind of signature all along, and that the truth lies not in brightness, but in a specific, anomalous rhythm of light? The analysis then ascends to a second level of interpretation. A positive detection would not be a single monolithic discovery, but a spectrum of possibilities. The first, and perhaps most conservative outcome, would be the identification of a faint, discontinuous stream of thermal emission points. These isolated knots of infrared light, strung along a projected path, would align tantalizingly with the historic passage of 3I Atlas. They would suggest a sporadic shedding of material, a trail of breadcrumbs left by a transient visitor. This would be a remarkable finding, confirming that interstellar interlopers can indeed seed our solar system with fine, detectable debris as they traverse the inner planetary system. It would transform our understanding of such objects from singular points of light into sources of ongoing physical interaction. But if this were the case, what dynamical processes could cause a small, fast-moving body to shed material in such a discrete, clumpy manner, and how long would such a tenuous trail persist before dissolving into the background? A third, and far more profound, level of analysis would be triggered by the discovery of a continuous, coherent ribbon of mid-infrared emission. This would not be a series of dots, but a smooth, unbroken stream, and its morphology would be the true key to its origin. If this thermal filament were observed to curve, not with the simple arc of a Keplerian orbit, but in a way that suggests a dynamic interaction, it would point to a phenomenon of greater complexity. Specifically, if it bends in accordance with the gravitational resonance at the edge of Mars's sphere of influence, it would imply that the dust is not merely passing by, but is actively being shepherded, trapped, and organized by the planet's gravity. This would no longer be the scattered debris of a flyby. It would be a structured feature, a permanent or semi-permanent ring or torus of fine dust held in a delicate dance with the red planet. The implications of such a structure would force a radical re-evaluation of the Martian environment and the processes that shape it. Is it possible that Mars, a world we perceive as largely isolated, maintains a delicate, invisible ring of captured interstellar material, a trophy from its gravitational encounters with visitors from the void? The confirmation of a eerie thread would carry transformative consequences, elevating the James Webb Space Telescope from a passive observer to an active guide. A clearly defined thermal trail would serve as a cosmic roadmap. It would validate the concept of dust logistics, the idea that fine particulate matter follows predictable, mappable pathways through the interplanetary medium. This, in turn, would provide a critical navigational tool for future robotic missions. A spacecraft, positioned in a high orbit around Mars, could use this map to rendezvous with and collect microscopic samples of genuine interstellar material, delivered and sorted by the solar system's own gravitational machinery. The JWST would thus become a pathfinder, its infrared vision charting a course for a new form of sample return not from a planet or asteroid, but from the river of dust flowing through our celestial neighborhood. But if we can indeed map these streams, what other cargo might they be carrying? And what secrets of galactic chemistry and the origins of planetary systems are locked within those microscopic glassy grains? This newfound ability to trace the thermal whispers of dust inevitably leads to a more pressing question. If we can map the stream, can we then identify the individual stones within the river? The delicate infrared thread, once confirmed, demands a deeper, more resolved investigation. It calls for a different kind of eye, one not sensitive to gentle heat, but capable of actively illuminating and probing individual, meter-sized targets within the flow. How then do we transition from mapping the vast, ethereal stream to locking our sights upon the singular, solid objects that may lie within it? The void between Earth and Mars is not truly empty. It is a realm of perpetual dust, a fine mist of cosmic debris that scatters sunlight and veils the inner solar system in a tenuous shroud. To peer through this haze, to reach out and touch the distant red sands, we do not rely on light alone. We employ a more assertive form of inquiry, a focused shout into the silence, planetary radar. It is the voice that cuts, through the dust, a pulse of coherent energy that travels for minutes across the interplanetary gulf, striking a target and carrying its echo back to a waiting world. If there exist objects of meter scale, these so-called micro-rocks, in the vicinity of Mars, their faint radar return, a ghost of a signal, holds a story. It is a narrative written not in amplitude alone, but in the precise, intricate dance of phase and polarization, a tale of shape, rotation, and perhaps of substance. The most powerful instruments for this celestial echolocation are the Goldstone Solar System radar, a terrestrial voice, and the Green Bank telescope, a colossal ear listening to the cosmos. Throughout the early 2020s, this duo has maintained a planetary radar capability of unprecedented sensitivity, capable of detecting echoes from objects that would have been mere noise just a decade prior. Simultaneously, a network of 8 to 10-meter optical telescopes in the high deserts of Chile and the mountains of Spain has been tasked with a complementary mission, capturing the reflected light spectrum of these same targets. This dual-pronged approach, initiated around 2023, provides a simultaneous chemical and physical fingerprint. The true breakthrough, however, lies in the technique of phase referencing. By using the exquisitely precise stellar positions catalogued in the Gaia data release 3 as fixed celestial anchors, astronomers can now pin down the position of a fast-drifting, faint target with an accuracy previously reserved for the largest planets. We are no longer just listening for echoes, we are triangulating the position of a whisper in a storm. How precisely can we map the ephemeral paths of these smallest wanderers? According to current models, the analysis of such a faint radar return follows a logical, hierarchical path. At the first level of interpretation, a weak and diffuse echo, one that scatters energy in all directions, is the signature of a natural, irregular surface. It speaks of a rough, pitted landscape, perhaps a fragment of a primordial asteroid or a piece of cometary debris tumbling mindlessly through the void. Its spectrum would likely show the familiar absorption bands of silicates or water ice, the common minerals of our solar system. This is the expected, the ordinary, the null hypothesis of cosmic detritus. But what if the echo does not conform to this simple profile? This leads to the second level of analysis, where the data presents a more complex puzzle. A radar return that is not a single peak, but a cascade of multiple shifting peaks, suggests an object undergoing a complex, perhaps wobbly rotation. Scientists suggest this could be due to internal mass distribution anomalies or the influence of external torques, such as the subtle but persistent Yarkovsky effect, where the asymmetric emission of thermal radiation from a warming and cooling surface acts as a gentle thruster, imparting a spin. It is the signature of an object under stress, a natural body responding to the immutable laws of physics. Yet, the precise pattern of that wobble, its periodicity or lack thereof, can reveal so much more about its internal constitution. Does its rotation betray the hidden fractures of a recent collision, or the consolidated strength of a monolithic structure? It is at the third level of interpretation, however, that the narrative takes its most profound and speculative turn. Here, the radar echo is not diffuse, but specular, mirror-like. It is a sharp, coherent glint, the kind produced not by a rough natural surface, but by a flat, unnaturally smooth plane. Such a reflection would be anomalously bright, a beacon in the radar data. When paired with a simultaneous optical spectrum from the telescope networks that shows not the expected mineralogical bands, but a flat, featureless, and chemically ambiguous signature, the conventional explanation begins to fray. This combination, a mirror-like radar reflection and a spectrally barren surface, defies the properties of known asteroids or comets. It points toward a surface that is either artificially smooth or composed of a homogeneous, non-silicate material, perhaps a manufactured alloy or a metamaterial designed for purposes we can only guess. Could the void around Mars be host to more than just ancient rock? The immediate implication of successfully phase-locking onto a meter-scale object of such anomalous character is a paradigm shift in our operational reach. To track such a target is to define its orbit with exquisite precision, and a precisely known orbit around Mars opens a door previously only contemplated in theory, the potential for interception and sample return. An orbital drone, a small, agile spacecraft already positioned within the Martian sphere of influence, could be programmed to rendezvous with such an object. It would be a mission of minimal energy expenditure, a gentle nudge to capture a piece of the Martian orbital environment and bring it into a dockable bay. For the first time, we would not be analyzing Martian soil or atmosphere, but an object that has been sharing the planet's celestial neighborhood, an object whose origin is, at this point, entirely unknown. What secrets of orbital mechanics, or of something else entirely, would such a captured sample reveal? This prospect, however, raises a deeper, more fundamental question that transcends the mere act of retrieval. If such objects are present, how did they arrive in their current orbits? The natural pathways of celestial mechanics are well trodden, governed by gravity and chance. But the identification of an object with anomalous properties compels us to ask not just what it is, but how it came to be there. The journey of a small body from the heliocentric swarm of the asteroid belt into a stable orbit around Mars is not a trivial one. It requires a precise and unlikely combination of gravitational perturbations and orbital resonances. The solar system is a vast clockwork, and its gears are unforgiving. Could the presence of certain objects in certain orbits be the result of natural forces alone, or does their configuration hint at a different kind of mechanics? This line of inquiry inevitably pulls our gaze from the specific target to the broader dynamical system, from the solitary echo to the symphony of forces that govern motion on an interplanetary scale. To understand the path of one, we must model the forces acting upon the many. If the objects we are detecting are not merely passive rocks but entities of a different nature, then the forces required to shepherd them into the Martian sphere of influence may extend beyond the gentle tug of gravity and the faint push of sunlight. The silent ballet of celestial mechanics unfolds in the void, governed by equations as old as time. To pull an object, any object, from the cold currents of interplanetary space into the gentle embrace of a planet's sphere of influence requires a precise application of force. The central question, then, is one of thresholds. What is the exact combination of gravitational tugs, the subtle push of radiation pressure, and the magneto-hydrodynamic forces of the solar wind required to bend an orbit, to redirect a wandering body so it becomes, even temporarily, a captive of the red planet? The answer lies not in a single number, but in a complex, dynamic interplay of physics, a delicate balance point we are only now beginning to map with any fidelity. According to current models, the sphere of influence of Mars is a volume of space where its own gravitational pull dominates over that of the Sunday. To cross this invisible boundary, an object must shed a specific amount of orbital energy. Mainstream planetary science posits that for the vast majority of natural interlopers, like small asteroids or comets, this energy transition is achieved through gravitational interactions over immense timescales, a slow and stately dance dictated by the n-body problem. The solar wind, a tenuous plasma flowing from the sun, is typically considered a negligible force on any but the most microscopic dust grains, its pressure far too weak to meaningfully alter the trajectory of a substantial body over a short period. The dominant force, the primary sculptor of orbits, remains gravity alone. But what if gravity was not the sole conductor of this cosmic orchestra? The speculative hypothesis introduces a far more dynamic agent. Imagine the interstellar object, 3I Atlas, not as a passive wanderer, but as a natural tugboat, a focal point generating a complex force field. Its own outgassing, a jet of vaporized volatiles, could create a localized plasma environment, interacting powerfully with the embedded magnetic field of the solar wind, the interplanetary magnetic field. This interaction could, in theory, create a temporary and extended wake of altered magnetic pressure, a low-density wave that could, in effect, lower the energy threshold for smaller, trailing objects to be captured by Mars's gravity. Could such a natural phenomenon act as an invisible command, herding a cohort of debris through resonant interactions? The evidence for such a possibility is being pieced together by dynamicist groups between 2020 and 2025, who have begun to merge classical N-body simulations with sophisticated magnetohydrodynamic models of the solar wind. These are not simple calculations. They incorporate Mars's high-degree gravitational field, updated in 2023 through 2025, with data from orbiting satellites, which reveals the planet's lumpy interior and its subtle effects on approaching trajectories. Furthermore, these models use the profile of the interplanetary magnetic field, calibrated against the Sun's own activity cycle, as a critical boundary condition. To benchmark their results, scientists use the well-documented flight path of another interstellar visitor, 2I Borisov, as a control. Does the path of Borisov, when run through these combined models, reveal any anomalies that pure gravity cannot explain? The analysis yields a stratified reality, a hierarchy of controllability. At the first level, we find that only micron-sized particles, fine interplanetary dust, are significantly and directly manipulated by the combined forces of radiation, pressure, and plasma drag. For these motes, the solar wind can act as a gentle breeze, slowly but surely pushing them across the void. They are the easiest to shepherd, their minuscule mass making them pawns of stellar weather. But if the force required is so small for these particles, what larger structures could they form that might, in aggregate, exert a greater influence? Progressing to the second level, the simulations suggest that millimeter to centimeter-sized debris, often the fragmented remains of cometary nuclei, can be guided, but only under very specific conditions. This requires a precise orbital resonance, a harmonic alignment where the periodic tug from the interacting plasma fields and the gravitational perturbations from Mars synchronize. In this delicate phase lock, small forces, applied repeatedly at the right moment, can accumulate to produce a significant orbital change, a phenomenon akin to a pendulum being pushed at just the right time to increase its swing. The object is not pushed, but led, its path coaxed into a new configuration. Is this resonant guidance merely a statistical curiosity, or could it be a reliable mechanism for delivering specific sizes of material to a waiting world? The third and most provocative level of analysis concerns decimeter-sized objects, small boulders that would normally be considered far too massive for any non-gravitational force to manage. The unified models indicate that even these VTANG, these wandering stones, could potentially be pulled into the Martian sphere of influence if a perfect storm of conditions is met. This would require an exceptionally powerful solar wind event, a coronal mass ejection of significant magnitude, coinciding with a period of intense and asymmetrical outgassing from the primary body, like 3I Atlas. The resulting magnetohydrodynamic shockwave and the rocket-like effect of the outgassing could, in concert, provide the impulse needed to nudge such a substantial object across the critical energy threshold. Could the cosmos, on rare occasions, assemble the necessary conditions to throw stones of a meaningful size from one system toward the grasp of another? The consequence of this unified modeling is profound, offering not just an explanation but a potential tool. It gives us a shepherd's map, a dynamic chart of the plasma currents and gravitational contours that define the approaches to Mars. This map becomes a manual for navigating these energetic pathways, a guide for future missions employing nanocraft designed to ride these very dynamical tubes, using the natural forces of the system to sail effortlessly toward the red planet. But if we can learn to read this map and ride these currents, what might we find already waiting there, delivered by the same natural mechanisms? This leads us inevitably to a new and critical consideration. As this hypothetical cohort of objects, guided by resonant forces and plasma winds, sweeps through the orbital space of Mars, it does not pass without a trace. Each fragment, from the micron-sized grain to the decimeter-sized boulder, is a potential vessel, a carrier of material from a place of unknown origin. The risk, then, is not one of collision, but of contamination, both forward and reverse. What happens when the pristine, if harsh, environment of Mars is seeded with foreign matter? We must consider the possibility that these objects carry exotic minerals, pockets of water ice with unique isotopic signatures, or, in the most profound and unsettling scenario, microbial life, should their origin be a biological one. The introduction of these materials could irrevocably alter the Martian environment, complicating our search for indigenous life and potentially triggering unforeseen chemical processes. And the danger flows both ways. A sample return mission from Mars, in the future, could inadvertently capture not just Martian regolith, but a stowaway from the depths of interstellar space, leading to a back-contamination event on Earth with consequences we cannot possibly predict. The Shepherd's Map, therefore, is not merely a navigational aid, but a biosecurity chart, outlining the pathways of both opportunity and profound peril. Are we prepared to manage the cosmic exchange that these dynamical tubes seem to facilitate?